So in this video, what I want to do is talk all about section 6.4. 6.4 is going to be all about derivatives of logs. And what we're going to do is we're going to figure out how do we differentiate logs, how do we integrate things that look like derivatives of logs, like how do we undo that? What does the chain rule have to say? And then there's going to be one more thing that we can do at the end. So just in short, the natural log is really going to be the only log that we have to study because all the other logs are equivalent up to constants. So if we can figure out how the derivative of the natural log works, then we can take the derivative of any log because we can write this using the change of base formula as the natural log of x over the natural log of b, the natural log of b being a constant. So once we figure out what the natural log of x is, we can go back and fill this in. Now, what I want to do to find the derivative of the natural log of x is exploit the fact that the natural log is the inverse of the exponential and that we know how to differentiate the exponential already. So we're going to use the fact that e to the natural log of x is equal to x. And what we can do is we can differentiate both sides with respect to x. And when we do that, let me write it just so it's clear what I'm doing here. We're taking the derivative of both sides. So the derivative of the left side is going to be itself times the derivative of the exponent, and that's what we're looking for. So this is itself times the derivative of the exponent, so the natural log of x, the derivative of x just being 1. And this implies that if I were to look at the e to the natural log of x, that's really just x, because we know that those are inverse functions, they undo each other. So this is x times the derivative of the natural log is 1, and therefore the derivative of the natural log of x is 1 over x. Okay, and so that's the main derivative that we know. And therefore, if I go back up to the top, the derivative of log base b of x is going to be 1 over log base b. So that's a constant that tags along, times 1 over x. And that's it. And if I were to take and apply the chain rule, then if I were to take, say, u as our function, and if I were to differentiate the natural log of u, what we would get would be 1 over the inside times the derivative of the inside. That times the derivative of the inside part is exactly the chain rule. Okay, and so that's what the chain rule says for us. And this really, first, let me say that this can be written as u prime over u. So the derivative of the inside over the inside, if you prefer to do it that way. But this is really the main result from the entire section. Okay, and so that's the idea there. That's how you differentiate natural logs. This answers a lot of questions for us already. With that in mind, let's do a few examples. So let's look at, if I were to take the function that's the natural log of e to the x plus cosine of x, the derivative of this function would be, you take the inside and put that in the denominator. So it's 1 over the inside. So 1 over e to the x plus cosine of x times the derivative of the inside, which would be e to the x minus sine of x. Okay, or you could write it e to the x minus sine of x all over e to the x plus cosine of x, same thing. If we were to take, say, sine of the square root of natural log of x. Okay, so here's one where the natural log is involved, but it's kind of buried in there in the function. It's a composite function. Then the derivative is going to be, I'm going to just at first think about this as sine of a function. And so the derivative will be cosine of that function times the derivative of the inside. What's the derivative of the square root of natural log of x? Well, that's the natural log of x to the 1/2 power. So the derivative would be 1/2 natural log of x to the negative 1/2, again, times the derivative of the inside, which would be 1 over x. So here we use the chain rule twice. Okay, but that's the derivative there. Simplify it to your heart's content. I'm happy with this. Okay. One other thing that I want to mention here, and one other wrinkle here, and this is just kind of a subtle point, but it comes up a lot. and it'll come up specifically when we talk about antiderivatives, is the following. So if I were to take the function that's the natural log of 3x, let's think about what the derivative of that function should be. So if I were to have the natural log of 3x, then the derivative is going to be 1 over 3x times the derivative of the inside. The derivative of 3x is just 3. Okay, and so we again end up with 1 over x. That makes good sense when you think about the log rules, that we know that this is just the natural log of 3, which is a constant, plus the natural log of x. So when you differentiate, the constant goes to 0. The reason why that's relevant for us is that if you remember, the absolute value of x is defined as a piecewise function, and it's defined as x when x is positive, and when x is non-negative, and negative x when x is negative. Okay, so that's the absolute value of x. And therefore, you can talk about, therefore, when you take and you think about the function, the natural log of x, when x is positive, the derivative of this function is going to be 1 over x. That's the function that we've been talking about all along. And if you take the function that's the natural log of negative x, when x is negative, then the derivative, again, is going to be 1 over x, because it's like having a constant. It's exactly like having a constant times x here. It's just the constant's -1. So the derivative is again going to be 1 over x. But this presents a slight wrinkle, a slight complication when we talk about anti-differentiation. What's the antiderivative of 1 over x? Well, if x is positive, so if x is positive, then the antiderivative would be the natural log of x. Okay, and so this is going to be the natural log of x if x is positive. And if x is negative, then this is going to be the natural log of negative x. And if we want to, and we do, I want to just write this succinctly as this is the natural log of the absolute value of x, of course, excluding x equals 0, because the natural log of 0 is undefined. So the integral of 1 over x is not just the natural log of x, it's the natural log of the absolute value of x. And that's going to be crucial for us. That'll matter in a few cases here. Won't matter in every case, but it'll matter in a few cases. So with that being said, let's do a few antiderivatives, and then we'll call it a day. So our antiderivatives, we're going to talk about, let's say we wanted to integrate. Let's say we wanted to integrate 4x over x squared plus 3. Okay, so let's say we wanted to do that. When we anti-differentiate, what we're going to do is we're going to notice that we have a linear term up top and a quadratic in the bottom. And so that should tell you that, it should at least give you a little hint here, oops, that we're going to substitute u equals x squared plus 3. And therefore du is going to be 2x dx. We don't have a 2x dx, we have a 4x dx. So there's a few different ways that you can handle this. But however you want to handle it, you're going to end up with 2 times the integral of 1 over u du. Because the 4x, if you want, you can write 4 as 2 times 2 and bring one of the 2's out, and then the other 2 gets incorporated in the du. Or you can bring the 4 out and then bring this 2 over, and you get 4 times 1/2. Okay, so whatever your algebra steps are to get here, this is the right place to go. This is going to be 2 times the natural log of the absolute value of u plus c. And then that's going to be 2 times the natural log of x squared plus 3 plus c. I can drop the absolute value in this particular case because x squared plus 3 is always at least 3, and therefore always positive. So I don't need absolute values there. And then this function happens to be defined for all x values. Okay, and so that's how we'll integrate with natural logs. Let's do one more. Let's look at the integral from 1 to e of the natural log of x squared over x. Okay, and so we're going to integrate this from 1 to e, and it's the natural log of x quantity squared all over x. I want to differentiate the natural log of x squared. Means that you take x, you take the natural log of x, and then whatever that value is, you square it. That is not the same. Be very careful algebra-wise. That is not the same as taking the natural log of x squared. So in the first case, you're squaring the natural log. In the second case, you're squaring x and then taking the natural log. Okay, and so those are different operations. So with that in mind, here we're going to substitute u as the natural log of x. Du is going to be 1 over x dx. This is a definite integral, so we might as well change our bounds. X goes from, so because this is a dx, x goes from 1 to e. So when x is 1, u is going to be the natural log of 1, better known as 0. And when x is e, u is going to be the natural log of e, which is 1. And so this integral is going to become the integral from 0 to 1 of the natural log of x squared, that would be u squared. And then our 1 over x dx is our du. And altogether, that's going to be 1/3. Okay, that's you got 1/3 u cubed. Plug in from 0 to 1, you got 1/3. Okay, so we'll do a few more things. I did kind of hint at that there was one more thing that we're going to do in this section. And let me just explain how that works. So if you were to have a function y equals, say, x squared e to the x sine of x, how would you differentiate this function? I mean, there's nothing that appears to involve natural logs here, except if you were to differentiate this, you could do the product rule twice and everything would be fine. There's a nice trick here called logarithmic differentiation. So logarithmic differentiation. And the idea here is what you're going to do is, instead of looking at y and taking the derivative, you're going to take the natural log of both sides. And the reason why taking the natural log of is nice is that the natural log turns products into sums, and sums behave much nicer with derivatives than products. So the natural log of y is going to be the natural log of x squared plus the natural log of e to the x plus the natural log of sine of x, because it's the natural log of a product, so that becomes the sum of the natural logs. Now differentiate. So this tells you that if we differentiate, we'll get y prime over y. And now these are trivial to differentiate. The natural log of x squared, the derivative is going to be 2 over x. The natural log of e to the x, that's just x, so the derivative is going to be 1. And the natural log of sine of x is going to be cosine of x over sine of x, or cotangent. Okay, and then finally, this tells you that y prime is going to be whatever this stuff is times y. We can move the y over. And so our y prime is going to be 2 over x plus 1 plus cotangent of x times our original function, x squared e to the x sine of x. Okay, and so that's, I think, a little bit nicer, especially when you get some practice with this. That gets quicker when you have 3 or 4 things being multiplied together. Rather than applying the product rule multiple times, you can get away with just logarithmic differentiation.